All right. Thank you for inviting me to talk about the Aria project today. So I'm going to be talking about the work of a large group of people from Caltech, from JPL, from the Italian Space Agency, and from the University of Basilicata. So Aria stands for Advanced Rapid Imaging and Analysis. And this is a project that we started about 4 or 5 years ago to try and improve our ability to use SAR and GPS data for hazard monitoring and response. And we started out looking at the earthquake problem, trying to develop products for earthquake response, but understanding that the capabilities and the tools that we were building would be applicable to other hazards as well. And so the fundamental thing that we're trying to do here is to make the SAR and GPS products and the integrated seismic products rapid and reliable so that they can be used for monitoring and near real-time assessment. So this involves automating a lot of the process and also working with end users that are not just the science community to understand what their needs are following these types of disasters. So the challenge of using this remote sensing, the SAR data for disaster response, one of the challenges is automating the processing so that we can deal with large quantities of data. We don't know when the next earthquake or volcanic eruption is going to be, so we need to be looking globally all the time. We also want to be looking at as large amount of data as possible so that we can understand the uncertainties in our data products and get a better understanding of exactly how well we can resolve the information that we're trying to provide. So in order to automate this, we've been using a system engineering approach. So we've been working with the data system engineers at JPL to develop a robust system that can be flexible for the type of data that we analyze. So for SAR data, as many of you know, there's lots of different types of missions, and they each have their own characteristics. So, and there's always people developing new algorithms to exploit this data for natural hazards. And so we want to develop a system that is easily adjustable so we can incorporate these new advances and also so we can incorporate new data streams. We also want to demonstrate these data products to the end user community, the decision support community. So as an example, we see here the damage proxy map here. Let me see, can I have a, yeah, there. So this is developed by Sang-Ho Yoon at JPL. So this is using coherence change as a proxy for damage on the ground caused by an earthquake. This is an example from the magnitude 6.3 Christchurch earthquake in 2011. You can see that days after the earthquake, there was an overflight by the ALOS satellite, and you would be able to use this overflight, comparing it to data acquired before the earthquake, to look for ground change. And this ground change can be caused by building damage, by liquefaction, or by landslides. And by looking at this earthquake, you was able to see that the mapping of the damage from the SAR satellite was very similar to the mapping of the damage done by engineers on the ground. Of course, that's a very time-consuming process. So it's very enticing to see that we could get this type of synoptic view of the damage from an earthquake just days, or basically as long as it would take for the next satellite pass to go over the area, and as long as it would take to then process that data following the event, as opposed to waiting months and months for the analysis. And these are just examples of how well you can, or the types of damage that you can see with this coherence change technique. So it also shows that you can not only see a synoptic view of the damage, but you can also look at the building scale level at damage. So you can see here the Christchurch Cathedral, the spire was collapsed, and this was detected by the coherence change. And then the landsliding here was also seen in the coherence change, as well as liquefaction. So one of the questions that we get when we talk about using SAR for damage assessment is how rapidly can you expect to get this information following an earthquake or another disaster? Because many of these SAR missions, they have repeat times of 16 days, 42 days. So you're not expecting another satellite overpass for some time from any one single satellite. But we like to look at the constellation of satellites. And while we don't have open access to all of this data, more of the newer satellites are having open access data policies. And Sang-Ho has looked at this, and if you look at how frequently one of these SAR satellites flies overhead, anywhere on Earth, at this point in time, a radar satellite passes overhead at least once per day. So the problem is really one of access and pre-existing data in order to use this SAR data for response. It's not necessarily one of having to wait for the next overflight. So we've been working on the infrastructure to be able to take this data rapidly, turn it around, and provide deformation products, damage assessment products. So this is a project that's been funded through NASA ESTO, and we've been working on developing the automated SAR processing system using a hybrid cloud system. So this allows us to work with on-premises compute resources for sort of the day-to-day processing, and then if we have a need to process a lot of data rapidly, we can burst out to the cloud and increase our processing capacity. So it's very elastic. And so this has been demonstrated over the past year. This is very useful for monitoring as well as response. We've also been developing capabilities for data discovery and access. So automating, notifying people when data is available, when data products are available, and also tools for searching within the large data set. There's a poster on Thursday that goes into the details of this data system, so I encourage you to go to that poster for more details. So one of the key aspects of working on this data system and really testing out the automation and developing the capability has been our collaboration with the Italian Space Agency to develop better capability for this hazard response with SAR. So using their data from the Cosmos SkyMed satellites, we've been working with them on developing advanced software and testing out and improving our capability with the data system to look at many different areas and many different types of hazards with Cosmos SkyMed data. So you can see here on this map of examples and areas that we're looking at, there's earthquakes, there's volcanoes, there's flood response, there's glacier dynamics, as well as landsliding. One of the key projects within our collaboration with ASI, though, is looking at California. So this is the CaliMap project, and they've been mapping California using ascending and descending passes so that you get repeat coverage of every region 16 days, and then for any one location, data is approximately collected once a week. And the Aria system, in order to keep up with this, has had to be downloading and processing the data automatically and continuously. So having this data set and working with this data set, it's enabled us to really test and refine this hybrid data system. We've had to burst out to the cloud in order to do some reprocessing as we're testing different INSAR strategies, different INSAR processing strategies. And it's also driving the development of the need for automated INSAR quality assessment. So typically people have been using INSAR data in a quantity that they can, within their own research group, they can do the quality assessment. But this is too large of a data set to really do by hand. So some examples of how we've been using the data for hazard response and hazard research, just how powerful this type of data can be. You can see here there's the magnitude 5.1 Habra Earthquake. This happened in March of this year. It's a relatively small earthquake, but the Cosmos SkyMed data is so good that we can see just 4 centimeters of displacement with this. And you can use this to help refine our fault models and understand what fault this earthquake occurred on and understand how that would affect the future seismic hazard in LA. We also responded to the Napa earthquake in August, and so we provided an interferogram within 3 days after the event. This was used by field geologists on the ground to try and locate surface ruptures. So it was also used by the USGS and EIC for improving their fault modeling of the event. You can see here a tweet from one of the geologists on the ground, Tim Dawson, locating a rupture at the airport. Here are some other areas where they were able to map surface rupture, breaks in the road due to the earthquake. And so this type of data can be useful for understanding what type of damage the earthquake has caused. For this somewhat small earthquake. You can see that, cracks in the road, they're not too severe, but imagine a larger earthquake, a magnitude 7 or a magnitude 8. There's going to be a lot more damage, and it's going to be a lot harder for crews to know where to go. So having this synoptic regional scale view of where the strain is highest will be extremely helpful following these types of events. There is a poster on Wednesday afternoon in the special session on the Napa earthquake that goes into more detail about our rapid response products for this earthquake. Here's an example using the damage proxy map algorithm that I described earlier at used for the Christchurch earthquake, looking at Typhoon Haiyan. So this was a response that we did last November, when Typhoon Haiyan devastated the area of Tacloban. We analyzed the Cosmos SkyMed data. This large red square here shows the region that was analyzed. And it's important to note that this algorithm is automatic. It doesn't require humans to evaluate the pre and post event image, as is necessary for most optical image change detection. So we're able to get a synoptic view of how much damage occurred over a very large region relatively quickly, as long as we have access to the data and there's pre-event data. So this here shows validation against an optical analysis. Because we hadn't worked in this area before, we wanted to make sure that what we were seeing was truly damage, because this was the first time looking at data in the Philippines. So this is comparing it to optical imagery, and you can see that it's actually hard to see the red squares mapped out by the optical change detection, because it overlaps with the red squares mapped by the SAR. Okay, thanks. Can I change? I'm not going forward. I need to speed up, and I've just slowed down. There we go. Okay, we can also look at deformation related to volcano hazards. So as many of you know, volcanoes tend to inflate before they erupt, and we want to be able to image this precursory inflation. And this can be done, and it's been done in many examples with SAR data. You can see also the co-eruptive deformation. So you can see the deformation from Kilauea volcano. Also, the INSAR time series shows the inflation at Capawe volcano and the Chile-Argentinian border, as well as an earthquake associated with Sabancaya volcano in Peru. Another more recent volcanic event, the recent Icelandic eruption at Barabunga. This image here, the deformation image on the ice, is from the CSK data. It spanned 1 day, and then this deformation here on the ground is from RadarSat data, which spans 24 days. So this was used to confirm that the caldera was collapsing, 40 centimeters of collapse in 1 day. So these are just the disaster events that we've provided demonstration response products for. Some of these were provided quite rapidly. Some of these were done after the fact, and they were useful for giving us an understanding of how much we can learn from this type of data, from the GPS data, from the SAR data. They're also useful for talking with decision support people, emergency responders, to get from them whether or not this information is truly useful to them, what format it should be in, and to also educate them that this type of data is available. Another way to do that we've been participating in is these earthquake simulation exercises. So the state puts on Golden Guardian exercises twice a year, and we've also participated in FEMA level or FEMA national level exercises to simulate earthquakes. We'll provide products to them so that they can see what sort of information they can get from this remote sensing data. And, because in an emergency is probably the worst time to introduce a new product. So it's important to participate in these exercises. We've done this with other projects at JPL. I think you'll be hearing about one of them later in this session. And this FEMA national level exercise was actually done with other NASA projects as well. So this is an extremely useful tool for getting information out to the emergency responder community and also getting feedback from them. So in summary, just want to say that Geodesy can provide a lot of information that's useful following a disaster. We've been developing this automated processing, which is very important in order to provide remote sensing information following a natural disaster. It's supported earthquake, volcano, and storm response. It's also supported natural hazard research. And just last point, it's important to work with these earthquake simulated exercises to work with the decision support and user community. And I'm just going to end with other presentations. I mentioned 2 of them, but these are actually other presentations going on at AGU later this week that are ARIA related. Thank you.